Hi, I'm Alex Kelly. I'm an assistant professor in the Department of Cognitive Science at Carleton University and a faculty associate with the Department of Computer Science at Bucknell University. I use they/them pronouns. Cutting to the heart of the question of how human memory discriminates between things you have seen before and things you haven't are two classic list memory experiments. The first experiment is the fan effect. In the fan effect task, participants study a list of pairs and then are tested on a set of pairs and must discriminate between the targets, that is, the pairs that were in the studied list, and the foils, the pairs that were not in the studied list. At test, participants are slower to recall or reject pairs with what is called a higher fan. A fan is how many times an item occurs in the studied list. For example, Hippie's store has a fan of 3 and 2. The theoretical principle of human memory that the fan effect demonstrates is that the more likely a memory is to be relevant to the current context, the more easy that memory is to retrieve. The second experiment we're going to be talking about is the extra list feature effect. In the extra list feature effect task, participants are faster to reject pairs with an unstudied item regardless of the fan. For example, even though Hippie has a fan of 3, it's easy to reject as an unstudied pair because school wasn't in the study set at all. The theory here is that the rejection of foils is based on detecting a contradiction between memory and the cue, and not based on familiarity of the cue. The fan effect and extra list feature effects pose a challenge for existing computational memory models. Computational memory models allow us to formalize our theories of how human memory works. While there are many models, mathematical comparisons of the behavior of these models reveal strong similarities. Humphreys et al. 1989 compared the pair recognition behavior of the Minerva, SAM, and Totem models of memory, as well as Humphreys' own matrix model. This table is a modified version of the table that appears in Humphrey et al.'s paper, extended to include ACT-R, holographic declarative memory, and the holographic exemplar model. In the table, alpha is the similarity of matching items, and beta is the similarity of mismatching items. The value of alpha is around 1 under ideal conditions, that is, minimal interference and good encoding, and beta should be around 0. This analysis simplifies the math of the models to capture the essential details of interest. Each memory model has studied a set of pairs xi and yi. The table shows the matching strength elicited from each model when presented 3 different cues: one of the studied pairs xi, yi, an unstudied pair of studied items xi, yj, where I does not equal j, and a studied item paired with an unstudied item xi, z. All matching strengths are expressed as a difference. The matching strength for a pair of unstudied items wz is subtracted from the matching strength of each of the 3 cues, simplifying the matching strength expressions by eliminating any terms that are common to all cues, such as the baseline activation in ACT-R. Thus, the matching strengths presented are a measure of the ability of each model to discriminate between a target and foils. We compare the matching strengths of HTM, ACT-R, and Minerva on the fan effect. ACT-R and HTM, as has been found in prior work, correctly predict lower matching strengths with larger fan. Conversely, Minerva does not predict the fan effect. For recognition tasks, Minerva uses the dot product as a metric of similarity between a cue and the pair retrieved from memory, called an echo. Using the dot product, Minerva correctly predicts that pairs with higher fan are more familiar. If we understand the matching strength as a familiarity score, the 3-3 test item is going to be very familiar, as we've seen both of the items in the test pair 3 times each in the study set. But the fan effect task is not a familiarity judgment task. Discriminating between targets and foils requires correct recall. For recall tasks, Minerva standardly uses the vector cosine, or the normalized dot product, as a metric instead. The cosine is constant across fans, failing to predict increasing difficulty with higher fan. Why does Minerva fail to predict the fan effect? The failure of Minerva to predict the fan effect is not an inherent property of the Minerva architecture. We reimplement HDM in a Minerva architecture to create Minerva HDM and find that HDM and Minerva HDM make the same prediction with only minute differences between the two models due to noise. We note that the ACTAR and HDM models use two memory recalls, a separate retrieval for each item in the pair, and adopt the same strategy with Minerva. When we do so, Minerva is able to correctly predict decreasing matching strengths with larger fans. To gain a deeper understanding of the behavior of the models, we perform a mathematical analysis. If we assume perfectly orthogonal vectors, the matching strength for a test pair that was in the study set is given by the equations shown, where F1 and F2 are the fans, respectively, of the first and second items in a test pair. Now that we can compute the exact values for the matching strengths for Minerva, we find that the model is not actually constant across different fans when using the vector cosine. In particular, Minerva 2 cosine predicts that the most difficult test item is the 1,3 fan with a matching strength of 0.988, an almost invisible contrast to the 0.990 or more matching strength of the other test items. So why would the matching strength in Minerva cosine be lowest for the 1,3 fan rather than the 3,3 fan? The answer to this question reveals what Minerva is doing. For Minerva, the additional items activated in memory for the 3,3 fan compared to the 1,3 fan serve only to reinforce the presence of the target in the echo, which improves similarity to the probe. Conversely, in people, having more lures in memory to sort through makes recall of the target harder, not easier. Thus, the reason that doing two separate recalls fixes the Minerva model of the fan effect is because it eliminates the mutual reinforcement between the two items in the test pair that make the 3,3 test pair easier than the 1,3 test pair. If the Minerva model is correct, participants adopt a strategy of making two recalls because the nature of the foils in the test set make it so that they cannot rely on judgments of familiarity elicited by a single holistic recall of the pair of items together. Given the strong mathematical similarities between the memory models, we can expect this result to generalize from Minerva to many of the other memory models we've considered here. If the models are correct, this means that when given a test item, such as hippie store, human participants choose either hippie or store and use that item as a cue to memory. What the participant recalls from memory is then compared against the other item, either hippie or store, and if it is a match, the participant decides that the pair appeared in the study set. It could be that any individual participant makes only one of these two possible recalls, hippie or store, for the pair hippie-store, and the fact that the response time is a function of the fans of both hippie and store is an artifact of averaging across participants. That participants are doing a recall for each item does not seem immediately implausible. Kwok, West, and Kelly, 2015, argue that evidence from a more complex variant of the fan effect task supports the hypothesis that participants only use one of the available cues at a time to make a retrieval, even when it would seem to be beneficial to use both cues. If individual response times are a function of the fan of only one item in each test pair, we should expect to find two clusters of response times for each test pair with unequal fans, one cluster that is a function of the smaller fan, and one cluster that is a function of the larger fan. Testing this empirical prediction of the two retrievals model is a matter of future work. The failure of Minerva to model the fan effect points to a larger issue with the Minerva model. In the extra list feature effect task, Mewhort and Johns 2000 tested participants with foils that have fans of 00, 10, 20, and 11, where 0 indicates that the item did not occur at all in the study set. Mewhort and Johns found that participants were fastest and most accurate at rejecting unstudied pairs and slowest and least accurate at rejecting pairs of mismatched but individually studied items. Conversely, for Minerva, the 2, 0 and 1, 1 foils are equally difficult because the sum of the fans are the same. 2 plus 0 equals 2, 1 plus 1 equals 2. For humans, a 1, 1 foil is much harder as we can quickly reject a 1, 0 or 2, 0 foil on the basis of a failure to recognize the item that did not occur in the study set. To account for performance on the task, Mewhort and Johns propose a variant of Minerva, the iterative resonance model, which incorporates a contradiction mechanism into the model's decisions. Introducing a contradiction mechanism allows IRM to make accurate response time predictions for the foils. IRM does not address Minerva 2's failure on the fan effect task. Adding a contradiction mechanism provides a means of modeling response times for foils, but does not fix response time predictions for the targets. However, an analysis of the vector algebra of IRM reveals a possible solution to Minerva's problem with the fan effect. In IRM, vectors are binary values of 1 and 0 indicating presence or absence of a feature. The echo in IRM is a vector of positive real values, indicating the strength of each feature in the echo. If enough features present in the probe are too weak in the echo, IRM decides to reject the probe as a foil. The response of Minerva to a probe is a distribution, and the echo is the mean of that distribution. What if human memory is sensitive not just to the mean of our recollections, but also the variance? When we say that a word is on the tip of our tongue, we not only know vague details of that word, but we also know that the details are vague. What if we are sensitive not only to the features of what we recall, but also how clear or certain those features are? In the echo of IRM, each feature of the echo has a strength. That strength is an indicator of the variance of that feature. If the strength is very high, IRM knows that the feature is present in the activated traces. If the strength is very low, IRM knows that the feature is absent in the activated traces. For intermediate values, IRM knows that the feature is only sometimes present. As demonstrated by the Minerva cosine model of the fan effect task, the mean of memory, that is to say the echo, is more or less constant across fan conditions. However, the variance of memory should increase with larger fan. A modification of Minerva that is sensitive to both the mean and variance of memory may be able to account for both Anderson's 1974 fan effect task and Mewhort and Johns' 2000 extra list feature effect task. This modification could be implemented using complex-valued vectors, such that the angle on the imaginary plane represents the content of a memory and the magnitude represents the certainty in that content. The proposed model is currently in development and results are a matter of future work. So, is there something fundamental missing from current memory theories, like confidence or contradiction or variance? Or is a change in memory recall strategy sufficient to well account for performance on these two list memory tasks? If the two recall theory is the correct one, we would expect to see participant responses on item pairs to be bimodally distributed based on the differing fan sizes of the two items in the pair. If not, there may be something more fundamental missing from current memory models. Testing this prediction will require further experimental work. Thank you for your time. If you have any questions, please reach out to me at alexkelly@cunet.carleton.ca.